Welcome to the deep dive. We're tackling a pretty significant topic today, climate intervention.
And specifically, stratospheric aerosol injection, or SAI.
Right, SAI. The basic idea for anyone needing a quick refresher is like putting up a giant planet-sized sunshade. You inject tiny particles way up high into the stratosphere.
To reflect some sunlight back out into space and hopefully cool things down a bit.
Exactly. Now, traditionally, the thinking around SAI involved, well, needing totally new kinds of planes, didn't it?
Yeah, the assumption was always specialized aircraft, ones that could fly really, really high, especially near the equator where the stratosphere is higher up. That's a big technical challenge.
A huge challenge. Felt very sci-fi, maybe decades away, but the research we've been looking at, it kind of throws a wrench in that.
It does. It asks this really interesting question. Could we potentially use the large commercial jets we already have for SAI, at least for certain types of SAI?
And what would that mean? That's what we want to unpack for you in this deep dive. We'll aim to give you the key takeaways, some surprising bits, without getting totally lost in the weeds.
Sounds good. So where this research gets really fascinating is its focus on injecting aerosols, but lower down than usually discussed.
Lower down? How low?
Up to maybe 14 kilometers, so still high, but not that high stratospheric level, often talked about. And crucially, doing it at higher latitudes. Think 60 degrees north and south.
Yep. Okay, 60 north, 60 south. Why there?
Because the tropopause, that boundary layer between the lower atmosphere, the troposphere, and the stratosphere above it, it's naturally lower at the poles.
Ah, I see. So you don't need planes that go quite as high to actually reach the stratosphere in those regions.
Precisely. Which leads to the possibility that existing planes, like, say, a Boeing 777F, the freighter version, could potentially do the job.
Wow, okay. Those big cargo planes.
Yeah, their maximum kind of cruise altitude is right in that ballpark, around 13, maybe 14 kilometers. So they could theoretically deploy aerosols in the lower stratosphere at those high latitudes.
That's quite something. Are there other options mentioned?
Well, the study also points to, business jets. A Gulfstream G600, for instance. They could fly a bit higher, maybe 15.5 kilometers.
But the payload would be much smaller, right?
Exactly. Much smaller payloads compared to something like a 777F. So you'd need many more flights.
But the big picture here, if we can use or adapt planes that already exist, that really changes things, doesn't it?
It potentially lowers the technical barrier quite dramatically. You're not talking about inventing and manufacturing a whole new aircraft type from scratch.
Which could mean, what? Faster deployment?
Potentially, yes. A much quicker timeline might become feasible compared to developing bespoke, high-altitude planes.
Which, raises all sorts of questions about accessibility, maybe even the risk of someone just going ahead and doing it unilaterally if the barrier is lower.
That's definitely a major implication to consider. But first, we need to look at how effective this lower-altitude, higher-latitude approach actually is. How does it stack up against the, let's call it, standard high-altitude idea?
Right, efficiency. How good is it at cooling?
So the research suggests that doing this seasonally injecting at 13 kilometers, 60 degrees north and south, it achieves about 35% of the forcing efficiency compared to injecting much higher, say, 20 kilometers year-round, closer to the equator, like 30 degrees north-south.
Okay, hang on. Forcing efficiency. Let's break that down. That's basically the amount of cooling bang you get for your buck, right? Per unit of stuff you inject.
Exactly. How much global cooling you achieve per unit of injected aerosol precursor, like sulfur dioxide.
So 35% efficiency. That sounds, well, quite a bit less efficient.
It is. It's a substantial difference. To put numbers on it, the study estimates that to get 1 degree Celsius of global cooling using this low altitude method, you'd need to inject about 21 teragrams of sulfur dioxide.
21 teragrams. Okay, and the high altitude way?
That's estimated at around 7.6 teragrams for the same 1 degree C cooling.
Wow. Okay, so almost 3 times the amount of SO2 needed for the same global cooling effect.
That's the calculation, yeah.
Which immediately makes me think, okay, if you're pumping 3 times more stuff up there, even if it's a bit lower, what about side effects?
That's the logical next question. And yes, the concern is that because you need so much more material, the risk of negative side effects, like acid rain, for example, would likely increase proportionally for the same amount of global cooling achieved.
Not ideal. Are there other downsides to this lower polar approach?
Another key point is the pattern of cooling. This low-altitude, high-latitude injection strategy produces cooling that's much more focused, more concentrated over the polar regions.
Which might sound good for, say, Arctic sea ice.
It could potentially help there, yes, But the flip side is it might be significantly less effective at cooling the tropics.
And the tropics are where many of the most severe climate change impacts are already hitting hardest.
Exactly. So you might solve one problem or help with one problem at the poles, but maybe not address the needs in the equatorial regions as effectively. It's a geographical distribution issue.
So it really matters where you inject, how high, and even when.
Absolutely. All those factors,
Yeah.
altitude, latitude, the season of injection, they all significantly influence how efficient the cooling is.
How so? What makes the difference?
Well, generally speaking, getting the aerosols higher up and into parts of the stratosphere where the winds spread them out effectively means they last longer.
Longer lifetime means more cooling overall.
Typically, yes.
Yeah.
Longer lifetime leads to a greater sulfate burden, just more of these reflective particles hanging around for longer. But there's a complication.
Okay.
It's about the size of the particles. The ideal size for reflecting sunlight relative to their mass is around 0.1 micrometers in radius. Tiny. But if aerosols hang around for a very long time, especially higher up, they can actually coagulate and grow bigger.
And bigger isn't better here.
Not necessarily. Bigger particles become less efficient reflectors of sunlight, and they can start to absorb more outgoing long-wave radiation from the Earth, which actually causes a slight warming effect, counteracting the cooling.
Ah, okay. Like a mirror getting dusty and a bit warm itself.
Kind of, yeah. Now, specifically for these high-latitude injections, there are other reasons they tend to be less efficient per unit.
Such as?
For one, there's simply less direct sunlight hitting the poles, especially outside of summer. And the surface below is often highly reflective already, snow and ice.
So the aerosols have less incoming sunlight to reflect back in the first place compared to over darker oceans or land near the equator.
That's part of it. The high surface albedo, as it's called. Plus, the study mentioned this strong seasonal signal for the low-altitude, high-latitude approach.
Seasonal, meaning it works better at certain times of the year.
Yes. The effectiveness, measured by something called aerosol optical depth, basically how much sunlight is blocked, peaks sharply in the local summer.
Why summer?
Because the chemical process that converts the injected gas, like sulfur dioxide, into the actual reflective sulfate aerosols requires sunlight. Photochemistry.
And there's just not much sunlight in the polar stratosphere during winter.
Exactly. So the aerosol production slows right down.
And I guess injecting lower down, does more of it just fall out or get rained out quicker?
That's another key factor. The study found that the lower the injection altitude and the lower the latitude, the more aerosols tend to end up back in the troposphere below.
Where weather happens, rain happens.
And they get washed out much, much faster. Their lifetime is drastically reduced compared to staying in the stable stratosphere.
So that really hurts the overall efficiency too.
Definitely. It's a major contributor to that 35% efficiency figure we talked about.
So boiling it down, this lower efficiency of the low altitude, high latitude method is mainly because
it's primarily due to less efficient aerosol production and significantly shorter aerosol lifetimes. Together, that means you just don't build up as large a concentration or burden of reflective particles in the stratosphere.
Less burden, less cooling power per ton of SO2 injected.
That's the main story. Other things like particle size and their exact location relative to sunlight play a role, but the lower burden is the biggest piece.
Okay, so technically possible with existing planes, but less efficient. Let's get practical there. You mentioned the Boeing 7777. How many planes are we talking about?
Right, the study did estimate fleet sizes.
Oh.
For that 1 degree Celsius of cooling using the low altitude 60 degree strategy, they calculated a need for about 102 modified 707 ZFs.
102. That's still a lot of planes, but maybe not an unimaginable number globally.
It's certainly fewer than the estimate for the high altitude strategy using new specialized aircraft.
Oh. How many for that approach?
The comparison number used in the paper was around 259 aircraft, assuming smaller payloads for those purpose-built planes.
Huh. That's really interesting. So fewer planes, but existing larger ones for the low altitude option, versus more planes, but needing brand new, smaller, high-flying designs for the traditional option.
It's a surprising trade-off, isn't it? Less efficient chemistry and physics, but potentially simpler logistics in terms of aircraft sourcing.
Which brings us back to that point about accessibility. Fewer planes using existing tech, that could make it seem more achievable for more actors, right?
It certainly lowers the barrier related to aircraft development and manufacturing.
Yeah.
Which, as you said, could mean more potential deployers' nations, maybe even non-state groups eventually.
And maybe an earlier start date becomes conceivable, which increases the chance of, well, someone just doing it, unilateral deployment.
That risk definitely seems heightened if the technical hurdles are lower. It raises huge governance questions.
Absolutely. And what about ground support? You can't just fly these anywhere.
No, that's a very real constraint. The study points out the challenge of ground infrastructure, especially for the high southern latitudes.
Antarctica and the Southern Ocean. Not exactly overflowing with major airports.
Right. There aren't many large airfields suitably located. You might need to build new ones in places like southern Patagonia, or undertake very long flights from further north, which eats into payload and flight frequency.
So maybe easier logistically in the Northern Hemisphere then? More existing infrastructure at high latitudes there?
Potentially, yes, although it's still challenging.
Okay, let's revisit the regional cooling pattern. We said it's more polar focused. Can we elaborate?
Sure. So concentrated cooling near the poles. Potential benefit for Arctic sea ice, maybe Greenland ice sheet. But the trade-off is likely less cooling felt in tropical and mid-latitude regions compared to a more globally distributed injection strategy.
And did the study model compare this directly with other strategies?
It did compare to different injection latitudes within its model. It found that even high-altitude injection at 60 degrees north-south resulted in less tropical cooling per degree of global cooling compared to injecting near the equator.
Implying that the low-altitude, high-latitude approach would have an even stronger version of that effect. More polar cooling, even less tropical relief.
That's the likely implication, yes. Less cooling benefit, where arguably it's most needed for billions of people in critical ecosystems.
It sounds like a really complex set of trade-offs. Before we wrap up, should we mention any limitations of this particular research? Caveats?
Definitely. Good science always acknowledges limitations. First, the simulations were quite short, just 2 years. So projecting the full long-term cooling effect involves some estimation.
Okay, what else?
They didn't include certain feedback effects, like how the aerosols themselves might change stratospheric wind patterns, which could then affect where the aerosols end up. That wasn't modeled.
Complex interactions.
Very. Also, they only modeled injecting sulfur dioxide. Other potential aerosol types weren't looked at, and they didn't explore if the longitude east-west position of injection mattered, which it might, especially at lower altitudes closer to tropospheric weather systems.
And the model itself?
They used just one climate model, the UK's SM1. Different climate models can give different results for SAI, so running comparisons with other models is always important for robustness. They also note their model's specific tropopause height might influence things.
Got it. So it's a really valuable piece of the puzzle, exploring this lower altitude option, but it's not the final word. More research needed.
Absolutely. The key takeaway is really that this low-altitude SAI, using existing aircraft types, seems feasible. It could deliver substantial cooling, and it's a big but, it comes with significant trade-offs.
Lower efficiency, meaning more material injected for the same cooling.
Which likely means increased side effects like acid deposition.
And a cooling pattern that's heavily weighted towards the poles, potentially leaving the tropics less protected.
That sums it up well. You've got the lower technical barrier, maybe faster deployment potential on one side.
Faces the lower efficiency, higher side effect risk, and uneven cooling on the other.
Precisely. And given the increasing conversations around climate intervention, this study really underscores why we need much more detailed research into these specific lower altitude strategies, their impacts, their risks.
It really does. This has been very illuminating, lots to think about. And speaking of thinking, here's something to mull over. If this kind of SAI using existing planes is significantly easier to implement, technically speaking, does that shift the focus? Should we be more concerned about the accessibility of these technologies rather than just their efficiency? And what does it really mean if unilateral deployment moves from a distant possibility to something potentially achievable much sooner by more actors? What are those geopolitical and ethical dimensions? Something to keep thinking about. Thanks for joining us on the Deep Dive.